And thanks to everybody for joining us. So IARPC is the Interagency Arctic Research Policy Committee, and it brings together leaders from many federal agencies, the departments and offices across the US federal government to enhance collaboration on research in the Arctic. So IARPC Collaborations is the public branch of IARPC, and it aims to facilitate the interagency communication, coordination, and collaboration to advance Arctic science. So as Hazel mentioned, IARPC released its current Arctic research plan last year, and earlier this week it released its biannual implementation plan. And in that plan, the modeling team will continue as a full-fledged collaboration team. So we're very happy with that. So the modeling team aims to enhance the understanding of the integrated Arctic system through the use of regional and global Earth system models. And in line with that, today we're going to be talking about Arctic regional downscaling. So regional models of the Arctic Earth system are valuable for scientists and other stakeholders. There's a lot of activity in that field. So we'll start off with a presentation by John Cassano, who's leading the Polar CORDEX activity, and he will give us an overview of that. So presentation about 15 minutes, some time for Q&A afterwards. Then we'll have a presentation by Wieslaw Maslowski, and hopefully we'll have some time for a more in-depth discussion afterwards. So with that, I'll hand it over to John.
Great, thanks, Wilbert. Yeah, so like Wilbert said, I want to give an overview of some international Arctic regional climate modeling activities. So Polar CORDEX being one, but Polar Res is a European project that I'll talk about as well. And I'm a professor at the University of Colorado in Boulder, but I also work with Wilbert and Wieslaw and several others on the call on the Highlight RASM project that's funded by DOE, which is my closely related project to the talk that I'm giving today. All right, so CORDEX, the acronym stands for Coordinated Regional Downscaling Experiment, and this is organized under WCRP, and then the link there can get you more information. And really the vision for CORDEX is coordinating science and application of regional climate downscaling internationally. And CORDEX has regional domains on all continents. Of relevance for us today is that Polar CORDEX has domains both in the Arctic, the top left, and the Antarctic, the top right maps. And you can find more information about the domains at the two links that I have on this slide. And really, Polar CORDEX has a couple of goals. One is to coordinate activity across different research groups and institutes to generate an ensemble of regional simulations from a suite of the different climate models, downscaling from a range of global climate models. And so I'll talk a little bit about that. But another goal, and I think probably just as important, is that Polar CORDEX brings together international regional polar climate modeling community and fosters collaboration and coordinated model-based activities looking at both polar regions. And so I'll talk a little bit about that as well. And really most of the work that we do gets done at annual workshops, usually held early in the fall each year. The meeting this year was in Bergen, Norway, at the end of September. The tentative plan is for a meeting in Utrecht in the Netherlands, either late September or early October next year. So the first goal for Polar CORDEX that I mentioned is this generation of archive of regional climate model simulations. And the most recent archive that Polar CORDEX has generated is based on CMIP simulations. And I'll just talk about the Arctic here today, but there's also a parallel Antarctic version. But the Arctic CMIP regional climate model simulations, there were 10 regional climate models that took place, and you can see them listed here, the second bullet. And this these 10 models downscaled output from 4 global climate models. There was a 50+ year historical simulation from 1951 to 2005 that was run by all the models. And then RCP scenarios, 4.5 was run from 2006 to 2100. Only a subset of models did this. And then RCP 8.5, the same 21st century simulation, all of the models ran that. And then the data for this is available at ESGF as well as from some institutional servers. And work is currently ongoing for CMIPS 6 simulations for polar CORDEX. But then the other activity that I said polar CORDEX really is involved with is coordinating international polar-focused regional climate modeling research activities. And so the next several slides, I'm just going to give you different presentations that were or a summary of the different presentations that were given at this most recent Polar CORDEX workshop in Bergen in September, just to give you a sense of the different things that this community is working on. So in the Arctic, there were several presentations about what I'm calling climate projection type work. So one was using storylines to predict climate change outcomes, and I'll talk in a bit more detail later on about what this storyline approach is. And then there were other presentations, one very high resolution 2.5 kilometer climate projections over Svalbard, a wind energy project looking at wind energy projections over the Arctic. One was focused on indigenous communities and providing climate information to Arctic reindeer herders. And then another was talking about developing new metrics to evaluate climate models. And then other presentations, so there were several related to extreme events. So one looking at extreme events over Alaska, another looking at winds over Severina Zamalia, and then finally a third looking at cyclones and atmospheric rivers and their impacts on Arctic sea ice. And then a couple of presentations on process studies. So one using Copernicus Arctic regional reanalysis, and then another looking at a parameterization for coastal drag and landfast ice. So those are all Arctic presentations. And then, like I said, polar CORDEX is bipolar, so there's Arctic and Antarctic. And then for the Antarctic research, there were several presentations on climate projection, so a parallel presentation to what was in the Arctic, looking at a storyline approach to Southern Hemisphere regional climate change, and then one looking at current and future climate simulations of the Arctic boundary layer, process studies, one looking at clouds and aerosols in East Antarctica, another looking at modeling blizzards in regional model RACMO. And then several presentations related to temperature extremes and surface melt. So looking at atmospheric drivers of surface melt over the Larsen Sea ice shelf from a modeling perspective. One looking at circulation associated with record temperatures at one of the Argentinian stations on islands off the Antarctic Peninsula. And then another looking at summer air temperature extremes over ice shelves. And then one that was interesting, looking at the impact of a total solar eclipse on temperatures in Antarctica. So a wide range of topics, both in the Antarctic and the Arctic, that the polar CORDEX community is looking at. But then another sort of big international activity that's going on for polar regional climate modeling is this polar regions in the Earth system, and the acronym POLARES. And this is an EU project. It's a 4-year project from 2021 to 2025. There are 16 European partners plus non-European collaborators, and there's about 8 million euro in funding for this. And the goal for this project is to provide more reliable and more confident climate information for impact assessment, both in the Arctic and the Antarctic. So it's very parallel to what polar CORDEX is doing. And then a couple of activities related to that goal is one, trying to fill in gaps in our understanding of how the polar climate system works and its position and role in the global climate system. And then the other, which I mentioned with a couple of the presentations from polar CORDEX, involves using what's called a storyline approach to generate useful climate projection information for end users. And I'll say that all of the information I have about PolarRes is courtesy of Priscilla Mooney. So PolarRes has several work packages associated with it. One focusing on Arctic processes, so that's helping to fill in gaps. Annette Rinke at Alfred Wegener and Timo Vima at the Finnish Meteorological Institute are leading this. And they're looking at things like cloud microphysics and aerosol and precipitation, atmospheric boundary layer over sea ice, snow and sea ice, and surface energy budget, sea ice drift in response to wind forcing, and then mixing processes and water mass transformation on the Arctic shelf. And then another activity work package within PolarRes is looking at how polar processes impact global climate. Dorth Handoff at Alfred Wegener and Lise Graff at Met Norway are leading this work package. And here, sort of the tools that are being used are models with variable resolution, so MPAS, variable resolution version of CESM, ICON, and ECAM6, running from sort of 10 kilometer to 100 kilometer scales. And the goal here is really looking at how local or regional processes in the Arctic have linkages to global climate. And one example here would be things like changing sea ice cover and turbulent fluxes and the impact that has on lower latitude weather. And then one of the bigger work packages is looking in the other direction from the previous one, which is how change in the global system is shaping polar climate. And there are several work packages here. So one is related to these storylines based on CMIPS GCMs, and this is being led by folks at Norse. Then there's an effort or work package related to high-resolution polar regional modeling, and then Ruth Mottram at DMI and Priscilla Mooney at Norse are leading that. And then there's a final work package here looking at polar impact assessment, and this is Hannah Lee at Norse and Nadine Johnson at the British Antarctic Survey. And so really the idea here is using storylines. And so the table on the right just shows some different sort of scenarios that the PolarRes group feel are important for understanding Arctic climate change. So, you know, looking at GCMs that either have strong or weak Arctic amplification, or you know, strong or weak warming in the Barents-Kara Sea, or in the southern hemisphere related to polar vortex breakdown, things like that. And so they identify these storylines that they feel are important. They find GCM simulations that sort of follow closely to that storyline, you know, either with strong Arctic amplification or weak Arctic amplification, and then use those GCMs that follow particular storylines to do downscaling. And then there's high resolution regional modeling that goes along with that. So they take the output from these global climate models that parallel the different storylines that they're interested in. They run an ensemble of high resolution RCMs, and you can see in the table here the different models that are being used and the components that are in those models. So all have an atmospheric component, but then some also have sea ice, ocean and sea ice components. Some are being run just in the Arctic, some are being run in the Antarctic, some are being run in both, and you can see the different partners that are involved with that. And the idea here is to use the regional climate models to downscale those global climate models and assess impacts in the polar regions. And some of the impacts that they're interested in, terrestrial, they're interested in changes in permafrost and boreal wildfires. Marine, so there's work looking at marine ecology and trans-Arctic navigation. And then the simulations they're running are being run at 10 kilometers. They're doing historical simulations, Forest with Era 5, that they're using to evaluate the suite of models. They're run from 1979 to 2022. And then they're going to downscale a single SSP projection from the GCMs based on the storylines. And these will be century-long simulations, again, at this 10-kilometer resolution. Okay, so that's PolarRes. And then to wrap up, and I only have a couple more that I want to talk about Polar CORDEX and future activities. So this was the last day of the Polar CORDEX workshop, some discussions about things that the community would like to do. And what I'll spend most of my time talking about is sort of coordinated model experiments and evaluation focused on Mosaic, the Arctic drift that took place from 2020 to 2021. And so I'll talk about that. And then there were some other suggestions, both for the Arctic and the Antarctic, that I won't get into here. And all of this is courtesy of Andrew Orr and Annette Rinke. So for the Polar CORDEX future activities, I think one thing that will likely go forward in the next year or so is using observations from Mosaic and using that to evaluate a multi-model suite of simulations, and doing this in a case study framework. So several of the case studies that are being considered, there's a cyclone event middle of November in 2020, where a cyclone passed north of Greenland, but there were 2 atmospheric rivers present, and that had a large impact on the surface energy budget. And the figure here is just showing differences in energy budget during the AR event, the darker colors, and then the climatological surface energy budget terms for that same time period, but from 1979 to 2021 from reanalysis data. And you can see the big impact this had on the surface energy budget. Another case from the spring, mid-April, was related with a warm air mass intrusion. There were a couple of atmospheric rivers with this as well. This also corresponds to a year of polar prediction targeted observation period. And so there'll be some additional observations beside what's available for Mosaic. And the interest in these cases, looking at how these lower latitude air masses transform as they move into the Arctic, looking at aerosol processes and clouds, boundary layer and how that's responding, and then implications for the surface energy budget. And then another possible case study is winter one, end of January to beginning of February, where there were a series of rapid temperature rise and fall events at the Mosaic site in the central Arctic. And the figure at the bottom just shows a time height cross-section from the end of January to the beginning of February of temperature over the lowest 2 kilometers of the atmosphere. And you can see this alternation between cold periods and warm periods over this span of about a week or so. And so scientific interest here is just contrasting these very 2 different winter states, clear and cold and warm and cloudy, looking at boundary layer processes, and again, looking at the surface energy budget to link up with sea ice processes. So if you want to get involved in Polar CORDEX, there are 4 of us that are coordinating Polar CORDEX. In the Arctic, it's Annette Rinke and myself. In the Antarctic, it's Andrew Orr and Christoph Kittel. Other CORDEX things that you may be interested in. So CORDEX is having their every 2 to 4 year international conference on regional climate. That's going to happen next September in Trieste in Italy at the end of September. And then there's going to be a Polar CORDEX workshop likely right after the meeting in Trieste. So folks that are coming from the US could go to the broader CORDEX meeting in Italy and then hop over to the Netherlands for the Polar CORDEX meeting. And I think that's all I have. So I will stop sharing.
Terrific. Thanks so much, John. That was an interesting overview of this this project.
Yep.
I'm pretty sure there are questions. So if anybody has a question, please raise your hand. Or also put your question in the chat. That's also a possibility.
Or do we want to wait for questions until after Wieslaw presents?
How about maybe a couple of clarifying questions, if there are any, and
Okay.
then we have a discussion after Wieslaw's presentation.
That sounds good.
Richard?
John, you mentioned the CORDEX archive. Is that available to researchers outside of CORDEX, and how would they get to it?
Yep. So it's mostly on ESGF. And to be honest, I'm not clear on the details of how to get to it. But if you send me an email, I can put you in contact with Annette, or you can send Annette an email and find out. But yes, it is open to people outside of Polar CORDEX as well. Yeah, we're a very open group. There's really no formal membership. People just show up at the meetings, present.
That sounds like if it's on ESGF, that it's organized something similar to CMIP experiments. Is that right?
It is. Yes.
Okay.
Yep. Yeah, the format of the data that's archived is in the CMIP format as well. So it makes it very easy to access or to work with.
It was a CMIP endorsed activity too, right? CMIP 6
Yes.
endorsed. Mm-hmm.
Yep.
Any other clarifying questions? All right, if not, then we'll hand it over to Wieslaw, and hopefully we have some more time to get back to this after Wieslaw's presentation. And if you have questions, then please put them in the chat, and we'll get to it.
Okay, can you see my screen?
Yes, you're doing.
Is it presenter mode?
Yes, sir. It's looking good. Thank you.
Okay, thank you. Thank you for inviting me, and thank you, John, for talking about the science and benefits of regional model. In this talk, I'll just basically present one case of a regional model that we have been working with, including John and people that are listed here on the first title page. The model has been is called Regional Arctic System Model, and has been supported for the longest time, and the majority of the funding by Department of Energy, Regional Arctic Climate, Regional and Global Model Analysis, but also by Office of Naval Research and the National Science Foundation. And we've been using computer resources from the DoD High Performance Computing Modernization Program. I'm listing my basically the RASM team here. I'm not going to read it with the affiliations. And the project has been going on for roughly 12 years now, and still doing relatively well, I guess. So in terms of motivation for regional modeling, years ago, looking at the CMIP-5 results, we've published a paper where we showed that even such basic features like the buffer high in the Arctic are commonly missed in the model. I'm showing, for example, in this case, the upper right panel, the negative color shown here is basically showing that the buffer high that was supposed to be in this location is basically absent in this model simulation compared to ERA 40. There are many other models that have problems as well. Some other models, they have a buffer high but in the wrong location. So basically, if your basic atmospheric forcing patterns in the Arctic are not well simulated, such as CMIP-5 suite of models, that will have an impact on the sea ice concentration and thickness and so forth. In a more recent paper, we've looked actually at the sea ice thickness distribution differences from CMIP-6 models. It's a paper published by my PhD student, Matt Watts, in Journal Climate 2021. And we've looked at a number of models relative to the Cryosat-2 estimates for a mean March 2011-2014. So basically, each panel is a map showing difference between the particular model, mean March of this years, minus Cryosat-2. Cryosat-2 ice thickness distribution is shown in the panel to the right. Can you see my cursor?
Yes, we can.
Thank you. And the two models that are commonly, considered to be kind of reanalysis, apology for that, is biomass, showing the difference from Cryosat, and we're also showing a RASM forced width analysis for comparison against biomass as well. So if you look at those scatter plots here, the CMIP-6 models relative to the Cryosat at the y-x-axis, most of the CMIP models, CMIP-6 models, are underestimating the sea ice thickness distribution in the Arctic for this 3 years in March. The biomass is showing some better agreement, but still underestimate the thicker ice relative to the Cryosat. And as a matter of fact, RASM, it's definitely not doing worse than the biomass reanalysis for those particular comparisons. So a brief summary of the RASM model configuration and setup. It's a regional coupled climate model. So we have most of the components that you typically see in the model: atmospheric components, sea ice, ocean, land. And we also have marine biogeochemistry, which was supported by the National Science Foundation. But the main feature of this is just we need global forcing data to do the dynamic downscaling in a regional setting. So this is an important thing, and I'll come back to this later. The map of the regional Arctic system model is shown in the upper panel here. The configurations are basically 50 kilometer or 25 kilometer atmosphere land. and 9 kilometer or 2.4 kilometer ice and ocean. The key message from the model setup is that we're not using data simulation. We're not doing any bias correction. And we're using the model hindcast to provide physically consistent initial conditions for the ocean and sea ice. And those results can be compared against observations in time and space. So if you look at our website, which is shown, the website in the upper right, and this is a forecast of September 22 minimum initialized on April 1, 2022. So the blue line is the it's ensemble mean. The gray shading is the ensemble spread, and the red dots are estimates from the NSIDC passive microwave sea ice extent. So you can see that in April initialized, we're off by maybe 3/4 million. Mostly the difference here, it's in the Sea of Okhotsk. By the time that we get into September minimum, RASM forecast ensemble mean is very close to the NSIDC measured specifically on that date of September 16. So this is a 6 months forecast, and RASM is showing a reasonable skill based on a 31 Mansell ensemble. If we go to a September initialized for 2022, we get a slightly better agreement, but not that better. It's very similar to what we got 6 months. And we're showing here the same comparison in terms of the sea ice extent prediction. So you could look at these results and say like, wow, the RASM is doing great. And I would respond not so quick, because if you look at the spatial pattern distribution, the observed pattern for September minimum from observations is shown in on the right, and the ice thickness and the ice area from RASM for that September minimum is shown in the left panels. So you can see that there's some significant differences in the Western Arctic, the Beaufort Sea, the Laptev Sea, and the East Siberian Sea, and maybe to some degree also in the Northern Barents and Kara Sea. So the actual message here is that good prediction of the sea ice extent number is not necessarily guarantee for a spatial agreement that when you look at the maps, you can see the differences. So that can be measured with something called integrated ice edge error, IIEE. And the left panel is showing basically a comparison of the CMIPS 6 models compared to the observed climatology, annual climatology of the sea ice extent with different colors. And basically the blue line is showing RASM comparison against observations. So we do have some biases which are focused mostly during the melt season. But if you compare it to CMIPS 6 models, you can clearly see an improvement with the regional model forced with reanalysis relative to the Earth system models shown with these other colors. The differences in biases are significantly larger, factor of 2 and 3 sometimes. If we look at the model optimization approach, we can improve some model biases that we have in our standard forecasting system right now. And I'm showing, for example, that we can improve the biases in the Sea of Okhotsk and also the Bering Sea, for example, that still exist in that simulation here where we're using the forecast system and hindcast to initialize it. But there's still some persistent biases, for example, in the Nordic seas, the so-called all-in. And in the summertime, you can see some biases in the Western Arctic and also north of the Barents Sea and Kara Sea. Those biases can be further improved when we increase model resolution from 9 kilometer to 2 kilometer, which are shown in the bottom panels. You can see that the biases that we have in the Barents and the Nordic seas are improved compared to the 9 kilometer model, both in winter and in the summertime as well. So increasing resolution also offers potential improvements as well. But I would emphasize that model optimization, which for some people might be a bad word, it's a process that helps you to improve your hindcast and forecast and biases in the model. So what we can do is also we can look at an effect of a single process improvement. So here we're showing comparison of the two different rheologies on the ice thickness distribution and the forecast of that ice thickness distribution. The left panel is showing the rheology called elastic and anisotropic plastic, and the middle panel is showing the standard elastic viscoplastic. The right panel is showing the difference between the two at the time of initial conditions, which was starting on July 1, 2019. So we have roughly 0.5 meter difference in the ice thickness on initial conditions. And if you look at the bottom panel for time series of ice volume, the difference in initial conditions that existed at the beginning of the run of the forecast basically persists for 6 months. That is not the case with the ice extent, which is shown in the lower left panel. The differences are very small, basically. So there is a large sensitivity in sea ice volume between the two simulations with two different rheologies, but negligible sensitivity in sea ice extent. So one conclusion you can draw is that sea ice is not a sufficient metric for model predictive skill. Another conclusion is that difference in the ice thickness distribution persists for 6 months at least in our simulations. So now we're showing some comparison with the mosaic data here. And let's start with the scatter plot, looking at the scatter plot between the mosaic Cryosat-2 SMOS combination with versus RASM sea ice thickness distribution for November 19. And then the bottom scatter plot is for January 2020. This is the wintertime development of the ice thickness distribution. The maps on the left are showing the respective November and January Cryosat-2 SMOS and RASM maps, and the differences are shown in the right panel maps, showing roughly 0.5 meter thickness difference in between the two maps. If you look at the statistics in terms of the mean and the standard deviation between Cryosat-2 and SMOS, actually between November and January, RASM is doing relatively well, both in the mean standard deviation as well as correlation. And the RMSD is roughly, as I said, 0.4, 0.5 meter, which keep in mind that it's comparable to the uncertainty in sea ice thickness estimates from the Cryosat-2. So another thing that we can do is just we can use the global model for downscaling and creating initial conditions and the forcing conditions. Here I'm showing the upper panels is the initial conditions from the CFSR as they are being used by NCEP to do the 7 months forecast. And the middle panel is showing the RASM, which was forced with the reanalysis from NCEP from 1979 through April 1, 2017. The right panel is showing the Cryosat-2 mosaic map for the time period centered around April 1, 2017. So you can see that the CFSR reanalysis is showing a significant problem in the Western Arctic in 2017 with ice thickness in excess of order of 4 and 5 meters in the Western Arctic in the Beaufort Sea, versus RASM is much more comparable to Cryosat-2 at the time of initial conditions. And then the bottom panel is the forecast of September 2017, so roughly 5-6 months later. The NCEP forecast is clearly showing the same persistent bias in September in the Western Arctic. RASM is showing a reasonable ice thickness distribution and the ice extent compared to the sea ice extent from the NSIDC shown here with the purple color, and the composite from Cryosat-2 for second half of September is shown in the lower right panel. So basically, dynamical downscaling is demonstrated here to reduce sea ice biases via increased model fidelity, including, for example, more realistic sea ice thickness distribution. And this helps to produce more realistic and physically consistent initial conditions that actually carry over at least 6 months into the predictions. So the other thing we did recently is that as part of the Highlight RASM project, as a matter of fact, we used the CSM Decadal Predictability large ensemble initialized to force the RASM in terms of the dynamical downscaling. I'm showing here a comparison of the ice concentration, ice concentration from the particular ensemble starting in 2009 through 2000 to 2009. CSM is in blue, RASM is red, and the NSIDC for that time period is shown as the black dashed line. So you can see that we initialize with more realistic initial condition compared to the observations, at least in terms of the ice extent. And the RASM in red continues to be in good agreement, both for the ice area, and this is the lower panel showing the comparison against Pyomas, which is not necessarily a final truth, but the CSM is showing biases in ice concentration and actually increasing bias in the sea ice volume for that ensemble, versus RASM is in good agreement with observations for ice concentration and keeps a similar difference against Pyomas for the time period of 10 years. So basically, dynamical downscaling of the initialized CSM DPLE using RASM, we've completed 10-member decadal ensembles covering 1955 to 2025, and it's showing the initial importance of the initial conditions, such as ice thickness distribution, again, for up to decadal time scale, not 6 months, as I mentioned earlier with the NCEP case. We're showing that those initial conditions might be actually important for up to 10 years. And RASM physics dominate the surface state, which doesn't carry apparent CSM biases, as it's shown in the volume panel here in the lower left from RASM simulation for that ensemble. If you compare the maps of the CSM versus RASM for another ensemble starting 2016 through 2025, so that's kind of like a forecast, you can see that CSM has a thinner ice in the beginning of that ensemble compared to RASM. But September actually is quite unrealistic. 2016 September has a very thin ice, less than half a meter, first year into the simulation, versus RASM in that year has a quite realistic ice thickness distribution. What's interesting is that 10 years later, September 2025, CSM has increased ice thickness compared to the first summer, versus RASM continued decreasing the ice area and volume after those 10 years in that particular ensemble. So the main thing is that initial conditions for each model are derived here independently from each other, and CSM generally shows less and thinner ice early on in that simulation, and more thicker ice after 10 years, which is not necessarily realistic according to what we know from the behavior of sea ice in the Arctic in recent time. So in summary, I just have those the panels here. I wanted to just basically say that regional optimized model physics improve initial conditions for subseasonal to decadal predictions and projections. And this approach has demonstrated improved subseasonal to decadal predictive skill of relevance to the Arctic stakeholders. Finally, I wanted to mention that model evaluation with multi-component data sets, including fluxes, not just state variables, is critical. So projects such as Mosaic are very important for not only model evaluation, but making improvements in the model based on process studies and parameterizations. I'll stop here. Thank you.
Excellent. Thanks, Wieslaw. That was really interesting. So I'll open it up for questions. So we have 15 minutes left for questions and discussion. I don't see anything in the chat right now, but if you have a question, then please raise your hand and speak up. And just to clarify that RASM is obviously one of the many regional system models that are around. And I hope we'll be able to continue this conversation in the next couple of years under the new Arctic research plan for IARPC. All right, any questions for Wieslaw or for John? Hilo.
Yeah, I have a question for John. on one of your slides talking about the potential storylines. Each thread seemed to have two contrasting stories. What is the purpose for that? Is that will be focusing on different season or different time, different period of years?
So I'm not directly involved with PolarRes, but my understanding is that rather than saying, let's look at, downscale an ensemble of GCMs that have all these varying responses to what's happening in the Arctic, I think the feeling in PolarRes is that it's more useful to provide stakeholders with information and say, all right, if the Arctic is, showing strong Arctic amplification, here's what you can expect, in your, for whatever aspect of Arctic climate you're interested in, if it's looking at permafrost or, reindeer herders or whatever. And so I think that's really the idea here, is that they have pairs of storylines to basically show, if the Arctic has strong Arctic amplification versus weak Arctic amplification, here's what you can expect as sort of the end result for whatever you're interested in. So that's my understanding of the storyline approach.
So maybe it also highly depends on which model.
Yes. Yeah, so the models that get downscaled are selected based on seeing, so they quantify, the degree of Arctic amplification across the CMIPS 6 GCMs. And then they say, all right, these are the ones that have strong Arctic amplification. Those are the ones that we downscale for this NH1A storyline, the top line in the table. And then they, take the ones and say, okay, here are the ones that have weak Arctic amplification, and those are the ones they downscale for that second storyline. Yeah, so they're not downscaling all of the ensemble of GCMs. They're just selecting certain ones that have these different storylines to it. So I think it provides a different perspective than just saying, we're going to downscale everything and throw out to the stakeholders this, ensemble with a bunch of spread to it that they maybe don't really understand how they want to interpret. So it's just a different way of getting at the uncertainty by saying, these different sort of stories of how the climate system's evolving.
Thank you.
I have a question.
Go ahead.
Yeah, I have a question to Wieslaw. I look at my model using trajectory, I think buoy, ITP buoy, to look at the trajectory individually, and also look at the vertical profile. And seem to me the comparison is really poor. So I don't know, you have done these kind of things before, this comparison of the trajectory comparison individually, and also I also compare with both of drier regions, vertical profile, temperature, salinity. Salinity is okay, and however, the temperature, the range is only from 0.7 to minus 1.8, and the Atlantic layer water smooth out, and also subsurface water also smooth out. So that means Atlantic water getting colder, and then the subsurface water getting warmer. So I wonder you have looked at this kind of the comparison.
So just to clarify, you're talking about the results that you were showing. You're saying that those problems occurred. This is from your model in the Arctic.
My model. Yeah.
Okay. Well, so I can tell you that we've looked at the in terms of ice trajectories. Comparison actually quite tricky, because if your winds is different, or a different detail, it's very easy to start drifting apart. And if you follow the same ice flow or piece of ice in the over long term,
Mhm.
they will definitely start diverging. This is an
Okay.
experience from the pre-mosaic. There's what is this experiment called? Comparison trajectory for the mosaic drift.
Mhm.
They've done a lot of those comparison, and in the end, they decided that this is actually something that requires more work in terms of improving model performance. But the main question I would pose is that whether this is a problem with the sea ice model or this is a problem with representation of the winds at the surface in the Arctic, which might be different than reality. So, but the main message or the response is that yes, there is of course a problem with comparison problem. Differences exist when you compare ice drift from the model with the ice drift from buoys.
Mhm.
As far as the upper ocean hydrography, many models have been diagnosed with spurious artificial vertical mixing in the upper ocean. So that's been quite well recognized, especially with the Z layers models. We have seen some simulations where we can have probably similar problems that the subsurface warm water in the Western Arctic is diffusing. We haven't seen any problems with diffusing Atlantic water. That's news. But overall, the idea is that what are the processes involved and whether those processes are properly represented. So I saw Mike Spall on the call before, and one of his papers, he demonstrated basically that the eddies in the Western Arctic are primary means of communicating the shelf water into the basin, into the Western Arctic. So if that subsurface water that is coming from the shelf, the Pacific summer water, or the shelf warm water locally, it's not properly communicated by mesoscale dynamics, you might still have a problem with that. So there's still process level studies and process level improvements in models that might be helpful. So for example, we've seen with the 2-kilometer model that we have a better representation of the eddies and the shell basin communications. And the hydrography in the upper ocean has improved compared to the 9-kilometer model. However, we haven't tried, enough in terms of vertical resolution. I think vertical resolution is another parameter that you may want to try to look at. The bottom line is that there is more work to be done, and there's still biases in any models. So what I would hope I presented is that we can do quite well without bias correction and data simulation with predictions up to 10 years. But we need to pay attention to model fidelity and representation of physics in the model, in particular components, but also in their coupling. I don't know if I answered a question, but
yeah, thank you. Yeah,
thank you.
I feel better. So otherwise, I feel it's I believe it's this common problem, but because my model is resolution is very, very low, vertical. So I feel okay. Thank you.
Thank you.
All right, thanks. Any other questions? Yes, I have a question for John. So many of the models, most of the models in the polar CORDEX, the Arctic CORDEX ensemble don't have an ocean or even a sea ice component, right?
Mm-hmm.
What are the implications of that? So is there concern about that? And what is what are you really missing by not including the ocean and the sea ice in these kind of simulations?
Yeah, I mean, I think, all of the things that we think about, when we worry about active coupling between the atmosphere, the ocean, and the sea ice are going to be missing. So, we don't have, I guess the things that I would think about or that, come to mind for me are thinking about storms, sort of rapid movement of ice, sort of changing area of ice in response to storms, changing upper ocean temperature as a result of, areas being exposed to, sea ice being removed and being exposed to these strong winds that you then get large turbulent fluxes coming out of the ocean into the atmosphere. And so, in the uncoupled models, you're missing all those things. The ice isn't moving in response to the presence of a storm. The upper ocean temperature isn't, dropping, it's just specified, it's not dropping in response to those storm events. And so I think those types of details probably are missing. And the question is, ultimately, how important is that going to be? My feeling as a meteorologist is it is going to be important that, integrated over all of the storms and everything that's happening, you're going to change what the atmospheric state looks like. And of course, the ocean, the sea ice state, which isn't being predicted or projected with these non-coupled models. But yeah, I think it's a concern. But, as, those of us that work with coupled models, it's a difficult problem. There's a lot of effort to it. And, what you're getting with these non-coupled models is basically just a higher resolution version of the atmospheric state that you see from the GCM, but you're missing any of the coupled changes that could affect that atmospheric state.
Right. So in any of the model analyses, evaluations that have been done then with this ensemble, are there very significant differences between fully coupled configurations and atmosphere only? Is there anything that really stands out?
I don't know off the top of my head. I don't recall.
Right. Great. Thanks for the clarification, John.
Sure.
Are there any other questions? I see two hands up. Wieslaw?
Sure. So I was at the meeting in September, Polar RASM meeting, actually. They do have some coupled models. AVI model, it's a coupled model, regional model. DMI model is a coupled model as well. And also they basically argued that they'll be looking at the CMIP models, which are coupled models as well. So they'll be downscaling atmosphere based on what CMIP 6 models show with their atmosphere. So they definitely Polar RASM is focused heavily on the atmospheric science, basically. And they will address some of the issues, but in terms of the coupling and the ice and ocean, but this is in minority in terms of objective and the storylines and so forth. So the idea is that when I was there, they're very much interested in teaming up with RASM, as a matter of fact, because we have quite a bit of focus on the ice and ocean.
Great, thanks. Richard?
So just following up on your question, Wilbert, it sounds like if they don't have an ocean model, that their focus is more on the atmosphere. Does this mean that they are looking more closely at cloud microphysics, for example, and do they have a representation of cloud aerosol interactions, things like that? Or is that a topic that they're looking at?
It is, yeah. So one of the Arctic process work package, one of the first ones they list is cloud microphysics, aerosol cloud interactions, and precipitation. So yes, they do have, and I don't know off the top of my head which models, but they are looking at, what differences in aerosol in the model is doing to cloud microphysics and cloud cover and precipitation and surface energy budget and all of those things. Yeah, so a lot of them are atmospheric scientists, like Wieslaw said, and that's where their focus is.
And related to that, do they look at stratosphere troposphere interaction, or is there, I guess related to this, is it common for them to be nudged or forced at upper levels?
I think almost all of them are nudged at upper levels. So
do you know how high in the atmosphere they go?
It varies. I don't know off the top of my head, but my guess is that they're not going very deep. If they're nudging at the top, you're not really getting any benefit out of having a deep model at that point, because you're just specifying from, your driving GCM or reanalysis.
Yeah. Okay.
All right, great. We're at the top of the hour, so maybe we should conclude the session. Thanks very much to John and Wieslaw for the very interesting presentations And as I said, I hope we'll be able to continue this discussion in the years to come. With that, Hazel, do you have any final thoughts to share?
No, thank you very much for the presentations and discussions. And we hope to see some of you on November 29th for the biennial implementation plan launch. Interested.
Thanks, everyone.
Thanks, everybody.
Thank you.
Thanks.
Thank you. Bye-bye.